So our second talk of the day is this paper called Orderlock. And basically, they say, what happens if you do RDMA over lossless and you start doing packet spraying? And you get a new type of deadlock that's called Orderlock. So the presenter is Weihao Zhang. He's a third-year PhD student in Shanghai Jiao Tong University, and he's advised by Professor Shizhen Zhao. And he's interested in data center networking optimization, RDMA, as you can see. So take it away.
Okay, thank you. Good morning, everyone. My name is Weihao Zhang, and today I'm excited to present our work, Orderlock, a new type of deadlock and its implications on high-performance network protocol design. It also includes Wenli Xiao, Yuqin Yang, Peirui Cao, and the corresponding author Shizhen Zhao. First, let's review the evolution of high-performance networking. Over the years, different workloads have driven different requirements. We'll focus on three key features. The first feature is in-order delivery, a requirement driven by TCP data centers. As we all know, vanilla TCP is sensitive to out-of-order packets. Guaranteeing in-order delivery allows us to improve hardware offload efficiency and simplify designs. Next, we have the requirement for lossless transmission. Lossy networks are less responsive, especially for short flows. And because lost packets requires retransmission, guaranteeing that the network won't drop packets can directly improve flow completion time. Combining the first two features give us RDMA networks. RDMA offloads the entire network stack to the NIC, completely bypassing the CPU. This provides us high throughput with low overhead. The third feature is driven by distributed AI workloads. AI traffic is latency sensitive, bursty, and has low entropy. The number and the diversity of flows for AI workloads are much smaller, and traditional flow-based load balancing are less effective. To handle this, we need fine-grained, aggressive, sub-flow level load balancing, which requires an out-of-order capability. The first two requirements gave us RDMA, and we now design a new protocol that is capable for AI and all other HPN needs and realize all three features at the same time. Unfortunately, the answer is no. We discovered that satisfying all three of these requirements simultaneously leads to a new type of deadlock, which we call Orderlock. Let's walk through what Orderlock is. Take this scenario. We have two different paths for flow to balance. These paths converge at the reordering buffer at the destination NIC or switch, where we do in-network reordering, which can hold a total of n packets for handling out-of-order arrivals. With sub-flow load balancing, packets are spread across both paths, but because these paths have different delays, packets may arrive out of order. In this example, packet 1 is delayed on path 1. At time t, the reordering buffer is waiting for the delayed packet 1 to maintain in-order delivery. Meanwhile, packet n+1 is just about to send on the other path. At the next moment, t+1, the packet n+1 arrives at the destination. This fills the reordering buffer to its capacity. With lossless transmission to prevent an overflow, the destination must send a pause signal upstream. Crucially, this pause signal blocks both paths, which also blocks the delayed packet 1 from ever arriving. And here is the deadlock. The buffer cannot forward any of its stored packets until packet 1 arrives due to the in-order delivery rule. And because of the lossless rule, it cannot drop packets to free up space. But for packet 1, it can only be sent once the buffer has space and the pause is lifted. This circular dependency is a deadlock. Orderlock is a self-blocked deadlock. Similar but different from head-of-line blocking, packet 1 is blocked by packets that were sent after it. But all the packets here belong to the same flow, so unlike the head-of-line blocking, it cannot be resumed. Other reordering methods, for example, reordering with VOQs, are also vulnerable, as long as you need to store the early arrived packets in a finite buffer. This risk of Orderlock exists. Our investigation further revealed that the simultaneous achievement of these three features is both a necessary and a sufficient condition for order lock. To demonstrate this, we developed a formal model. We model a network protocol as two functions acting over packet sequences. A transmit function describes how packet order can change as it travels through the network, and the receive function describes how the receiver handles such sequence and deliver it to the upper layer. We model this as partial functions. This means that they are only defined for valid input sequences. For abnormal sequences that cause an error or deadlock, the function's output is undefined. For example, a PFC deadlock is such state for the transmit function. Using this model, we can formally define our three features. In-order delivery means that for any two packets in the final delivered sequence, their original sending order is preserved. Lossless transmission is simple. No packets are lost. The number of packets remains the same after both the transmit and receive functions. To define out-of-order capability, we first need to quantify it. For any given packet, its out-of-order arrival level, or OA, is the number of late packets that arrives before it, where they must be stored when we perform reordering. The max out-of-order arrival, or MOA here, for a sequence is the highest OA value among all the packets in the sequence. With this, we can define out-of-order capability. For reordering limit n, the protocol allows out-of-order transmission with MOA greater or equal than n. This brings us to the formal definition of order lock. At the order lock state, the receiver function cannot yield a legal result without breaking the in-order delivery condition or the lossless transmission condition. Our paper further proves that combining the three ILO is the necessary and sufficient condition for order lock. You can find the detailed definition and proof in our paper. So, how serious is this deadlock? If order lock were rare, just like PFC deadlocks, perhaps we can just detect and recover from it. To find out, we simulated several popular packet spraying schemes on a factory topology. We found that per packet spraying solutions trigger order lock, and they do so at an extremely high frequency. With a 64-packet reordering buffer, order lock can even occur within the first 100 packets. In the example figure, three figures, 3 order locks occur within a single millisecond. Further simulations and testbed evaluations consistently show that order lock triggers at an extremely high frequency. This makes the traditional fail and recover strategies completely impractical here. The performance degradation would be massive, as every flow would constantly be entering a recovery state, which will devastate its FCT. And this leads to a question about the reordering buffer size. Packet spraying isn't a new idea, so why is this such a problem now? Bandwidth delay product, or BDP, is often used as an indicator for estimating buffer requirements. As shown in this figure, for traditional tail-dropping networks, the number of packets in the network will not exceed BDP. Even in lossless networks with flow-level load balancing, the in-flight packets are still bounded by BDP, plus the en route buffers, as they maintain a first-in and first-out order. But the situation completely changes when we combine lossless transmission with per-packet load balancing, because different paths can be paused for unbounded amount of time. The sequence number range of the in-flight packets has no limit. A BDP-sized reordering buffer is far from enough. We measure the reordering buffer required to prevent order lock and find the distribution has a very long tail. Making the situation worse, such requirements grows with the flow size. This means that simply increasing the buffer size is insufficient to prevent order lock. The conclusion is clear that running an order lock risky network is impractical, and protocol design must avoid it. So let's turn to a case study, design a practical high-performance network for AI workloads. Since combining I, L, and O is the condition for order lock, we can create an order lock-free network by breaking at least one of these 3 conditions. This leads us to 4 kinds of design approaches. Due to the high performance penalty, mature protocols are all order lock free. we have examined existing approaches to see how they either implement these features or work around with missing features. This allows us to categorize the 4 categories into 3 groups: limited out of order, lossy RDMA, and orderless delivery. Traditional limited out of order approaches primarily uses flow-level load balancing, like ECMP, FlowLead, and online flow rerouting, such as Conweave. As we have discussed, these flow-level methods are less effective with the low entropy AI workloads. Another approach in this category is credit-based flow control. This allows we to spray packets but use credits to ensure that the number in flight will not exceed the reordering limit. This enables fine-grained load balancing, but if the reordering buffer is too small, the sender will be self-throttled, limiting the performance. Next is lossy RDMA. Standard selective repeat mechanisms are incompatible with out-of-order networks, as such mechanism cannot recognize if a missing packet is truly lost or just have delayed, leading to unnecessary retransmission. Protocols like NDP improves on this by using packet trimming to explicitly mark dropped packets. However, just like CBFC, performance is throttled if the reordering buffer isn't large enough. Meanwhile, lossy means retransmissions, which can still harm FCT, especially for short flows. Finally, there is orderless delivery, where we simply ignore the reordering techniques. One way is to write directly into the unlimited host memory, but this is very difficult to implement in real-world engineering. Another approach is to modify the application, since for many AI workloads, the exact packet order is not critical. We have measured their performance through simulation and estimated the competitive ratio when being used for training different AI models compared to the ideal switch. It leads to conclusion that orderless delivery yields the best results. And if the buffer is not constrained, NDP and CBFC may also achieve satisfactory performance. In conclusion, our works make 3 key points. First, combining in-order delivery, lossless transmission, and out-of-order capability is the necessary and sufficient condition for Orderlock. Second, operating under an Orderlock risky network is impractical due to its high frequency and large reordering buffer requirements. And third, through a case study, we show that from our perspective, orderless delivery would be very beneficial for future AI-ready HPNs. Thank you. Any questions are welcome.
Done.
Okay, now it's open. Okay, great. Thank you for a interesting talk. So I have a quick question. So I'm wondering why this problem exists. Like when we have out of the receiving at the link. So usually we have both the bitmap and the reorder buffer, and usually the size of the bitmap matches the size of the reorder buffer. So that if your reorder buffer only have n capacity, and when you receive n+1 packet, and that will exceed your bitmap size first, and that packet will be dropped. So even with lossless network, like traditional RDMA NIC, they still allow the packet drop at the receiver NIC if the buffer is not is not enough. So if we allow the packet drop at the receiver side, when the out-of-order degree exceeds the bitmap size, so we will still have this problem.
Oh, thank you. Very good question. This means that we break the lossless condition to realize to break the order lock, and
yeah, but I think that depends on how do you define the lossless, because like usually we call lossless is at the switch side you are not your packet is never dropped because of congestion, but here you drop the packet at the receiver NIC because you don't have enough space for receiving. and that even exists in current ARNIC.
Yes, we don't take lossless just for congestion lossless. We take this for the whole network. As if you're dropping packets for congestion or dropping packets for breaking order lock, they all need retransmission. And we see the current NICs are supporting these features by just dropping packets, and they might achieve nice throughput within tiny flows, but their good put can drop to about 20% with relatively large flows because order lock are triggering, and we break the order lock by retransmission, and the retransmission takes a lot of time.
Okay, thank you.
Oh, thank you.
Hi, Ayush from ETH. Yeah, I thought first of all, very interesting work. I thought the analysis for the tolerance for the amount of out of order packets and the buffer size needed was very interesting. What I'm wondering is if you've done a similar analysis for in-network ordering schemes, because that analysis seemed to assume that all the ordering happens at the end host.
Yes, that's also a good question. We have in our, let's change it to my slides. And in-network reordering, such as SQR, we have seen it from previous literatures. They use in switch queues to perform reordering. But we think these are still cannot exempt from order lock, as you need to reorder, and you need to place those packets that arrived earlier inside some kind of like queue or buffer, and these are limited. And since they are limited, we may hit the limit, and hitting limit causes order lock.
Really nice analysis. Again, I agree, it's a nice presentation. People seem to have backed themselves into a corner with a particular type of AI. So when we did stochastic gradient descent, we could deal with loss and out of order, and the system still converges. So there are a bunch of AI large-scale systems which don't care about ordering because you can change the order of the computation. So if you receive parts of the updates in a different order, you just do the execution of the local receiver in a different order. So I wonder if somebody needs to go back and look at the actual computational architecture, not the protocol. I think your analysis is absolutely sound, but the requirement that the 3 requirements you put on the protocol come out of an application semantic in distributed computing, which is very, very brittle. And it seems to me that somebody needs to rethink the whole of this particular corner of AI about the computation. I don't know if you think that's a possibility, or is it just not possible in this world?
I think for when in old time.
Yeah, and dropping data there. Okay.
So, yeah. Yeah, very quick question. You actually did a very clever presentation because you answered the hard questions in your presentation, right? So I just have a quick question. So for this order lock to happen, right, you have necessary condition, right? So multi-pass transmission in order delivery and lossless, right? Have you ever got any chance to talk this idea with any industry, whether this condition necessarily can hold in practice? That's just a quick question, right? Because like people, you said you can very easily avoid this by invalidate one of these condition, right? Necessary condition. But have you ever talked to industry about this?
Oh, okay, thank you.
Yeah, very quick.
Our work is like a preliminary analysis, and we see that for industry, they have different approaches, and like OpenAI in the last 2 days, they use packet trimming, which means we cut off the lossless transmission. And for other companies, they may take lossless as, they want to deploy them in the original RDMA network stacks, and they may drop the, let me think, they want to drop the in-order delivery part because they are just compatible with our original RDMA hardwares, but they need a very niche changes in their model training or collective communication libraries. I think the industry.
Excellent discussion. Obviously, this paper will generate some heated discussion even afterwards. Let's thank the speaker again.